Good morning and welcome to this Monday, where we are continuing our discussion on optimization. As I am just setting up, getting our problem book ready, can I get confirmation in the chat that you can see and hear me? Whoopsie, put that there. Just get the YouTube chat open here. It's a little slow. Okay, let's get our problem book open. All right, so last time we did problem 10.2 as an example, where the function was given to me, the variables were defined for me. So the first part of the word problem solving steps were done for me. So it's not really a full question in terms of practicing. So let's move on to 10.4 actually, where just words are given making the question and we have to do everything. So that's a little bit more representative of what a test question could be like. You're building a fence to completely enclose part of your backyard for a vegetable garden. You have already purchased material for a fence of length 100 feet. Using that, what is the largest rectangular area that this fence can enclose? 4. So what I always like to do here is visualize with a little diagram just to get my thoughts in order and see what I have and what I'm working with. Not everyone likes it, but it gives me time to just see, okay, what am I working with? I'm working with a rectangular garden, so let's just emphasize that it might not be the same length, right? Rectangle, all right. So I'm going to have to define variables for the length and the width. So let me call this X and that's Y. I'm just planning right now. So the diagram on its own is not a sufficient definition of the variables that I'm going to use. It helps me, but I have to say, let X and Y represent the dimensions of the garden. And then I can point the reader to the diagram as shown, but I need a sentence. The diagram alone is not a definition of a variable, even though I think it is. In terms of the creator of this solution, it's not. You need a sentence at the very least to say, go look at the diagram to help understand which variables I'm going to use. So on the record, I have said this now. You need a sentence. All right. So now I know what X and Y represent. If I look at my question, I have 100-foot long fencing to use. So that means the fence is going to go all the way around. It's going to be the perimeter of the garden. So then what I know, write words, make it easy to read, that 2 sides for every variable, so 2x plus 2y is going to equal 100. Because all the way around the garden is 100 feet of fencing. That is what the question tells me. Then they want to know, what is the largest rectangular area that I can get? So I am interested in area. So I need to define another variable for the area. Now we're going to use the obvious A, but because it's obvious to me doesn't mean it's obvious to everyone. Let A represent the area of the garden. You don't have to write your sentence super detailed, but you need a sentence. Any variable that's going to be used need to be defined before I use it. Then I can say, oh, I'm going to have an area function. And the area is obviously x times y, right? So I have my 4 main problem-solving steps. And if you don't know what they are, go back to the very first lecture. Define the variables. Then step 2 is set up an equation, or in our case, in this kind of question, set up the function. In this case, it's going to be the area function. But now, step 3 is going to be the sort of solving step. In this case, I want to find the maximum area. But if I look at this function, this area function depends on 2 variables. And when I've done my analysis, increasing, decreasing behavior, finding critical points, whatever I want to do, it's always a function of just 1 variable. So I'm kind of stuck here. And that is where this extra piece of information comes in. That I can solve one of the variables with this equation. And in this case, it's going to be 100 minus 2x over 2, or 50 minus x. And then put that in my function to eliminate one of the variables. So my area function is then going to be a function just of x, which is going to be x times y is replaceable with 50 minus x. And there's my area function. I can simplify that, but I don't really know at this stage necessarily what I'm going to need it for. So it doesn't really matter right now. What matters is I need to have a function of just 1 variable. Because taking the derivative of a function with 2 variables, that's a whole other story. And not a calculus 1 question at all. So now at this stage, so let me number this. I had my number 1 step, define things I'm going to use. Let's sort of up to here. Then my second step, come up with a function and maybe clean it up a little bit. Just to illustrate that we are following those 4 main steps. Now at this stage, when I have my function, it might be useful to think, are there any practical restrictions? Because if I look at this function and ask it what its properties are and everything about it, it doesn't know where it comes from. It just says, I'm a function, I'm quadratic, this is what I look like, I continue forever, I'm defined everywhere, great. I have to think about the practical restrictions, the use of this function in the context of the question. So don't overthink it, but there is a limitation on the values of x, of course, right? X can't be negative. I can't have a negative length here. So at the very least, I am going to just say x has to be a positive number. I'm not looking at this too closely and thinking about, oh, how much space do I have for my garden? Certainly not infinitely long, but there's no indication that I can cut it off any further. So just be aware that there are practical restrictions. Don't overthink it, but I am limited to just positive values of x. And I need to be aware of that, because in some more difficult situations, maybe I get a critical point with a negative x value. That doesn't mean anything to me for this question. So in more complicated functions, that could very easily happen, and I need to be aware which x values are applicable to the question. Okay. All right. Now we can move on to step 3, where we're actually solving or doing what I need to do. In this case, it's not really solving an equation. It's finding where does this function have a maximum. Now, it's a very simple function. I can verify it by graphing it and whatever, but soon it might not be, and I can't rely on that. So I want to find the critical points. So find critical points of the function, because I know that is where, apart from the endpoints, which I sort of have awareness of, but there's no hard endpoint. I just have to have positive values. We'll get to that in a second. Apart from the ends of the interval, the critical points are the only places where a maximum or minimum can occur. So that's what I need to do. So for that reason, I'm going to take the derivative, and I don't need to see this as a product rule, right? I could just multiply the x in, because I want to have my basic properties, power rule, and those guys. So my derivative is 50 minus 2x. Nothing complicated in this case, of course. Let's start with nice and simple questions. Okay, let's see here. So I do my check for critical points. Let's do it over here. I check where is the derivative 0. Now I do check where is the derivative undefined, but that's not going to be the case here, right, for a polynomial. But I do have to remember that both of them could give me some x values. So for the 0, I might want to, I don't need to, I could just set this equal to 0, and then solve for x. Let's maybe have some space over here, and that is going to give me x equal to 25. So that is the only point that I'm getting out of this. It does fall in my interval, so I want to consider that. And in this simple case, for sure, that's probably where the answer is. But I want to be thorough in my summary here of all things I need to consider, x values, and then area values. Of course, there's no y, that is my y value, so to speak. So what I like to do is put an interval where I don't have an equal sign, right? X can't be 0, then I have no garden. I just want to remind myself that it's not an endpoint I can actually get. I can have a very small x value, but I can't actually get 0 when I don't have an equal there. It's an open interval. You can also write it like this, of course. Open interval, I do need to be aware of the endpoints, because in some complicated cases, the best situation might happen as I get close to this quote-unquote end value. It's very rare for us. We'll try and keep things simple. So I put it in brackets to remind myself I can't actually have a 0, but it is the end of my interval. And then I have my 25, which I can actually get. So when I look at the top here, like so, and I look at my function in whatever form, the x times 50 minus x is a convenient one. As x gets closer to 0, as I'm getting to the left side of my practical interval, this first factor is going to make the whole thing approach 0 as well. And I'm looking to find the largest area. So it kind of makes sense that as I reach this extreme, as the length of the rectangle gets really, really small, my area is going to shrink as well. if I just look at the infinity next, if the length of my area gets really, really big, because I have a limited amount of fencing, now I could have made this infinity something else, right? I could have made it 100. But just in concept, as it gets really big, the width of the rectangle is going to shrink down. And I'm going to get something that approaches 0 as well. You could update this. Some people don't like the infinity here. You could have said that, look, let's just look at this practically. Let's look at the rectangle. I have two x lengths here. I have this bottom one and this top one. And I only have 100 length for my fence. So if I ignore the y values and pretend they're 0 for a second, the longest x can be is 50. So you can update this, and maybe some people might feel a little bit better about that. So let's do that and put a 50 here. Sometimes I don't really care. Well, sometimes it's easy enough to find a hard number there. But still, I can't really actually have x equal to 50, right? Because then I've used all the fence. And I have no width, so I have no garden. So I still don't have an equal here. But if I look at it this way, maybe it's a little bit easier to wrap your head around. And let's update this guy as well. I still want to have it in brackets because I can't actually get there. But now I can maybe more easily see that if x approaches 50, then this bracket is going to approach 0, and it's going to make the area very small as well. So my best area is not going to sit there. 25 is the only point that's left. My area is going to be 25 times 25. Well, let's throw something on the chat. It's a little quiet in the chat. When I plug it in, it's obviously 625. And looking at all the places where an extreme value can occur, obviously this middle one is my best situation, looking for the largest area. Important. So just a little concluding sentence. The largest area of 625, and that'll be square feet, is obtained for a garden with dimensions, well, I have x. I kind of need to know y as well, right? For that, I can go up here and see, oh, 50 minus x is what y is equivalent to. When x is 25, y is going to be 25 as well. So it's going to be a 25 by 25 square. That is going to give me the maximum area. And you are done. So again, I want to focus on these 4 problem-solving steps. They change with the specific topic, but they're always there. Define your variables. Set up an equation or a function, depending on the situation. In this case, it's a function. Then solve what you need to solve. In this case, we're looking for the largest area. Where that occurs is going to be a critical point. Considering the endpoints, make our table, pick the best one. So it's quite straightforward. And then just wrap things up with a concluding sentence. Nothing that should be overwhelming in terms of the steps you have to go through. Often, what people struggle with is just forgetfulness, I think. And they don't pay enough attention to steps 1 and 2. They just think, well, obviously the area is going to be called A, so I'm just going to use an A. Yes, because we have some repetition, we do get used to using the same letters for certain things, but technically your answer has to stand alone and not assume the reader knows anything. You have to define all those variables. All right, next, let's look at problem 10.5. A fence of length 100 feet again is to be used to enclose 2 gardens this time. One garden is to have a circular shape and the other should be a square. Determine how the fence should be cut so that the sum of the areas inside both gardens, or just all together the sum, is as large as possible. So we have a very similar situation. But you'll see that in this one, some interesting things come up, making it definitely worth investigating. So let's just like before, have a little diagram. There's my circle, and there's going to be my square. And see, what do I need to define here as variables? I'll need to define a radius, let's call it r, and I need to define a side length for the square. Remember, they're both, all the lengths are the same. Let's call that x. But a diagram on its own is not enough, so I need to have a sentence or sentences that help me define it, or define it with the diagrams helping me. And the sentences can point to the diagram. Let R represent the radius. Ooh, come on, my writing should be somewhat neat. Radius of the circle, and x the side length of the square, and I like to write as shown to point the reader to my extremely talented diagram. Then I've noticed, of course, even at this early stage, that I'm looking to make the area as big as possible. So I know that I'm going to work with an area function, which means I need to define the name. Let's use the familiar a. Maybe not familiar to the reader, so I need to define it. Let a represent the total area. Okay, so now I am ready to move on to my second step, where I need to make the function that I'm going to be working with. Now the total area is going to be obviously the area of the circle plus the area of the square. Now these are formulas that we should of course know. Anything about a circle, area, circumference, and anything with a rectangle. A square is just a special rectangle. So the area of the circle is pi r squared, plus of course the area of the square, x squared. So at this stage, perhaps, it might be useful to start thinking about practical restrictions on these two r and x. This one is a little bit more complicated than 10.4. Now, it's not necessary that you have to think of it at this stage, but it's maybe the easiest when I have the variables and they're defined very clearly. So my extreme cases, my endpoints, definitely I need both of these quantities to be positive, right? But there are maximum restrictions on what they can be as well. So let's just put that in a side note here. Both r and x should be positive. But if I look at x first, maybe, what is the largest that x can be? Well, they tell me that my total amount of fence is 100. Now, the largest x can be, I'm going to get that when I have the biggest square possible, which is when there is no circle, or the circle is teeny tiny, 0, essentially, as close to 0 as I can get. And because that's not excluded in the question, in the wording of the question, it doesn't say I need to have both. I'm going to put an equal sign here in this case, because I could have a 0 radius, meaning that the circle portion of the garden is non-existent, and I just have a square. Or I can have x be 0, and then I just have a circle. And those are sort of the extreme cases. So let's just look. Let's just write this out to make it easier to follow. If my radius is 0, that's technically going to correspond to an extreme case. Then I have the largest x. So then, let's say here, largest possible x value. Because I need to now think outside of what the function is doing. The practical restrictions I need to manually think about. It's not going to be an automatic thing from a function. So the largest x will be when I have the largest square, which means when there is no circle. I'm using all the fence for the x. I'm using all the fence, so just like before, all the way around the rectangle. It's 4x in this case. And that's going to be the 100. That's a very curly one. The 100 feet of fencing. So that means x is maximally, the largest it can be is going to be 25, because I have to have a square. Okay, so I could put here x is going to be no greater than 25. I can get 25. I can get 25 by having no circle. I'm always using all the fencing, and then that is as big a rectangle as a square as I can get. It isn't the same as before. Because I have a square, I don't have a rectangle which have variable dimensions. Then on the other side, if I don't have a square and all the fencing is used for the circle, then I'm going to get the largest possible circle and the largest value of r. If I share the fencing between the two gardens, then I'll have a smaller radius value and a smaller x, of course, as well. The largest radius is going to be when there is no square, just a circle. So then I'm using all the fencing for the circumference of the circle. Circumference is 2 pi r, and that's going to be 100. So r is going to be 100 divided by 2 pi, or I can simplify that to 50 over pi. It's a little easier to see it at this stage, perhaps. So I can include this over here. R can be at most 50 over pi. Not as obvious when I look at the 50 over pi, but when I reason through it, it makes sense. What is the largest radius? Well, all the fencing is used for the circle, making it as big as possible. And then the circumference has to be the fencing, and I get the radius that corresponds to that, 50 over pi, whatever decimal that may be. So I have these, oopsie, that's a little close. I have these restrictions that I will remember at any stage when I ever need them. Maybe I just need one, maybe I need both at this early stage, because the radius and the side lengths are so easy to understand. It might not be a bad idea to look at them right away. But I have the issue mathematically now that if I'm going to find a critical point, I'm going to take the derivative. I can't do that with my skill set and my knowledge with a function that has two variables, which this one currently has, which is where the fencing comes in again. Now in general, without these extreme values, something in the middle, the circle portion, area, and the square portion will be there. And the perimeter and circumference of all of them will have to be my 100 feet of fencing. So the circumference of the circle plus the perimeter for the square, that's going to have to be 100. I'm always assuming I'm using everything, because using less fencing will never give me the best area possible, the highest area possible. So I'm going to max that out. Now you can decide which one do I want to eliminate here. Let's go for r, why not? So 2 pi r equals 100 minus 4x. So r equals 100 minus 4x over 2 pi. I could simplify that a little bit more if I really wanted to. And why not? It's not hard to do. 50 minus 2x over pi. I'll put a little circle around that, circular shape, so I can find it easily when I need to. And now you can look at the function by putting this equivalent expression for r, but in terms of x, into the function. So now I have a function that just depends on x. Of course, I could have solved for x, then I would have a function depending on r. The goal is it needs to be a function of only one variable. Which one you choose, in the end, it doesn't matter. So pi times this whole thing squared plus my lonely x squared, which didn't get any modification. Now, knowing that I have to move on to the derivative very soon, I want to clean this up at least a little bit. So I'm going to get pi squared at the bottom. It's going to cancel with one of those. I'll have my 50 minus 2x, everything squared, then over pi plus my x squared. And maybe that's good enough, right? The derivative doesn't need more. I don't have to multiply this out. I could, but I don't really see the benefit in doing that. Now, of course, you can remember here, now this is just depending on x, and remember that x is going to go from 0 to 25. 0, and then essentially I'm getting the area equal to the area of just a circle. 25, and you see this first one falls away, that's the circle portion, and I just have the area of the square. Now, we haven't calculated those areas, which we will eventually when we have to list the endpoints and the critical points that we get. So it's good to just keep in mind. I plug those in and we'll get I'll get the area for just a circle, just a square, which I need to consider as the endpoints, of course. So this seems good enough. Next, I will find my derivative because I need to find the critical points, right? Now I just have a constant 1 over pi in front, or I could leave it at the bottom. It's not a quotient rule because the denominator is constant. And I have a little chain rule here, not a super big deal. Bracket squared, derivative is 2 times the bracket. And then the second part of the chain rule says times the derivative of that inside bracket function, which will be a -2. And we'll clean this up in a second. Then the derivative of x squared is, of course, 2x. So let's maybe make this look just a little bit better. I have a -4 over pi. Maybe I like to keep that in front. I'm sticking to this bracket, not multiplying in and creating more pi coefficients. I don't like that. And I don't want to put in a decimal version for pi because then I have to round it and that might lead me to errors I'll miss. So I want to leave things as clean as possible. That's clean enough. Now this is a polynomial in x. Polynomial. And because of that, I know that when I check my critical points, the undefined check is never going to happen. So the derivative is going to be 0 when I set this thing equal to 0. Let's do that and see the equation that we are working with. Plus 2x here equal to 0. Let's not get distracted by everything else. So now I'm going to have to, I'll multiply it in. Why not? I get, do I have to? It doesn't actually matter, does it? No, technically I'm not going to multiply it in. I'm going to make this as clean as I possibly can. But an option was to multiply it in, of course. Now, some people struggle with simplifying these equations simply because it's been a while, maybe, and they're not super confident. So I'll write a few steps just to show I'm moving that to the other side. Then I'll divide by this negative 4 over x. 4 over pi, of course, which means multiplication by the reciprocal, which means, let's write that over here, negative, no, other way around, back it up, where's my button? Dividing by negative 4 over pi, which means multiplying by the reciprocal, negative pi over 4 on both sides. And what I'm saying and what I'm writing does not seem to be the same. So I therefore get just the bracket, and I can simplify some stuff here. 2 negatives, a 2 cancels with one of the 2's in the bottom, so I get a pi over 2x. 2 negatives, 2 with the bottom 2 left over, and a pi at the top. Then I want to move the 2x to the other side, maybe, and flip everything around to give me pi over 2 plus 2x equal to 50. I'm trying to stretch this out on purpose because I know some people aren't super comfortable with these things. And if I skip too many steps, some people might feel like, whoa, what just happened? And I want them to follow, right? I don't know how comfortable you feel with these things. I don't know what you remember, how detailed your review was, all those things. So let's just see. That's my accurate version of x, but I may want to, of course, just see what the decimal version is. When I present it, the decimal version is nice. So let's see here, 50 divided by bracket pi over 2 plus 2, close the bracket. What do I get? I get 14.0025 if I round it. And if I need this in a future calculation, I might type all the decimals or use this detailed version, which I can simplify if I want to, but I don't care. But for presentation purposes, I like to round to 4 decimal places, though it depends on the requirements of the question. I'm going to try and fit everything in here. So this is my critical point. Okay, critical point. Now it's maybe nice to find the corresponding R value here, because yes, I can go back to this function over here and plug x in. There's nothing wrong with that. Some people like to do that. Totally works. Or I can find the radius and go to the even cleaner original function. It doesn't really matter, does it? You see the radius is right there anyway. So let's maybe mix it up and do it that way. I'm going to, for presentation purposes, if my critical point is where the answer is, I'm going to have to find and state the radius that corresponds to that anyway. So it's 50 minus 2x plus pi. Now, just in the interest of saving time and MathBot not working anyway, let's see. I have done all these before to check. Now, of course, I can't find it. It's up here. It is 7.0012. Please verify. and that is when I put in this in the circle. 50 minus 2 times x, which is 14 point something, divided by pi. Okay, there it is. MathBot doesn't want to show anything in the screen right now. So let's maybe make a new page here. I don't want to try and squeeze everything in when I don't need to. That way we have a lot of space and no issue at all. Okay, so this is my critical point, or point location. And I will definitely have to find the area. But I also have to make a summary of, let's say maybe x. Maybe I want to go to the original function, whatever version works, right? So my critical point was 14.0025 rounded, and r was 7.0012. Very close, but those decimals could matter. Now let's find the area, which the version using r and x is up here. I'm just looking to see if I have done that somewhere. Pi r squared plus x squared, and I got 350.0620 when I rounded. Okay, so this is my critical point. I also have to remember to check the endpoints. Now one endpoint is when r is 0 and x is 25. So 25 and 0. That's the best I can do if I leave the circle and just focus on x, the square. Then we have a very simple area function because the radius portion falls away, and I just have 25 squared, which is 625. So that is one endpoint. If I focus on my x version of the function, that'll be the right endpoint. And the left endpoint is when x is 0 and r is 50 over pi. X is 0, the best radius then, using all the fancy 50 over pi, whatever that is. Then I get an area of just, let's go up here, just the circle portion, pi r squared, and x is of course 0. I'm just looking at my calculations here. Pi r squared, did I do that anywhere? You know, I don't know if I did. Let's see if MathBot is hopefully, actually isn't that super easy? Just in case MathBot doesn't want to work with me. Isn't pi radius, oh no, let's see, I'm gonna have a pi anyway. Okay, fair enough. I thought I could just do it in my head, but the pi is messing me up. Let us see. I thought I could get around MathBot because MathBot doesn't seem to want to work right now. But it's simple enough. It should do it right like that. I know I don't need to. 50 divided by pi, bracket, and then a square, pi times 50 divided by pi and bracket squared. Okay. MathBot would be really nice if you work with me just this once. I appreciate it. 795.7747. And this is the other endpoint. If I focus on the x values, then it would be the left one, the left endpoint. But now this shows something very interesting. That, like, I don't know what this function looks like. And I don't really care that much, to be honest. because it's not just the function, which clearly has one critical point, it's some sort of parabola, but it's also where the endpoints sit in relation to that. And the endpoints give me function values that are more, which you might feel makes a little bit of sense, that I get a better area if I don't try and split the fencing to make two different shapes. If you imagine gluing or merging these together, you can save some of this middle fencing by making one shape and getting the same kind of area with less fencing, so I can get a bigger area with the original fencing. But being restricted to just a circle then, or just a square, I don't know which one is better. Turns out just the circle is better. So let's say here, just the square, just the circle. So I do have to check the endpoints, because in these practical situations, things are a little bit more complicated. And I don't know what's going to be the best. Just because I find a critical point doesn't mean that's necessarily the answer. So let's write a concluding sentence here. The largest area of 795.7747 square feet is obtained with just a circle of radius 50 over pi. I guess let's calculate this guy. One more time, MathBot. He seems to have warmed up a little bit. 50 divided by pi. And of course, as I say, this is going to let me down. I know it. He waits for the most important times when we're so close to the end. No? Okay. Let's write it over here. 15.9155. 15.91. Didn't we find the radius already? Who's this guy? No. Sorry, that was a critical point. Never mind. That's not the best. This one's the best. Never mind. Feet. Okay. So critical point was maybe interesting. I could split it up. But I actually, with my fencing restriction, can't get an area as big in total as if I focused and specialized on just one little garden instead of splitting it up into two. Interesting. So, moral of the story is, check your endpoints. And do it early, perhaps. If I wait until this X version, the single variable version, to me personally, it's a little less obvious looking at this. What are the practical restrictions on X? Well, the whole point is to not look at the function. It doesn't have any restriction, but to think about the actual practical situation. And the simplest is where the function is in its original form. Having two variables, that's okay. They're related in some way. If I think about it practically, how big can I make X? And how small can I make X? Well, if X is 0, that means the other variable, in this case, is as big as possible. And then what does that mean? Very interesting things. Check your endpoints. Don't neglect them. When I can actually attain those endpoints, the optimal value could actually sit right there. So we'll look at more examples. There are some variations where I don't want to maximize area, but maybe the fencing costs a certain amount, and I want to design something in a way that the material cost is minimized. So we'll look at those kinds of questions next time. But in the problem book, there are a lot of slight variations even on this that you may want to but we'll continue this.